Okay, this will be the last lecture in the series of lectures where we are discussing the entity relationship data modeling process. And I am going to use our good old airline reservation example to initiate the discussion. So, the context that we have here is a customer trying to make flight reservations, and behind the scenes, there's this structured collection of data, which is our database. And the journey, the data modeling journey, began with some narrative description of the business application, from which we first, in the modeling process, first developed this logical model of the structure of the database represented as an entity relationship diagram. Notice, still now, I haven't really in detail discussed the process of going from the narrative to the logical entity relationship model. What we had done, in fact, is taken the model as if it was given to us, and we used that to introduce and discuss the various concepts, constructs, and symbols that are used in drawing this particular diagram. So this picture tells a story. So that was the first phase of the journey. And now we're in the second step of the journey where we are translating this logical model, the entity relationship diagram, to a more implementable structure called the physical model, the relational schema. And you remember from the first class, we talked about the relational model and how it's a relational database is a collection of relations. We had talked about primary keys, foreign keys, etc., etc. So we are in the process of translating. This is the second phase. We are translating the logical entity relationship diagram into a physical model, which is the relational schema, which will be implemented. And in this second stage, where we are doing the translation, what we have discussed so far is you have the entity relationship diagram. Those the two major parts of it. One is an entity, something called a relationship or a relation. And we had a detailed discussion of what it takes to implement an entity. So an entity has attributes, an attribute have certain something called an attribute domain. What values can the attribute take? And there was a discussion of all the different dimensions of this attribute domain. So what's the data type, what's the policy on null values, etc., etc. So there were different aspects and those details that we have discussed so far. So in this particular lecture, we'll complete that second stage of the transfer by discussing the second half of an ER diagram. So we've discussed the E, the entity, how to implement the entity. So in this last lecture today, which will wrap up our discussion of this journey, we'll discuss the second aspect of an ER diagram, namely the R, the relationship. So we will see now in today's discussion, we will see how relationships, namely these lines, how are they translated, how are they implemented in the relational schema. So that is what we are about to embark on. And I'm going to again, use this particular, as and when needed, we will see how the relationships will get translated. So just as a reminder, this is the logical model, the ER diagram, and in the previous lecture that we had, I had pointed out that there are entities. These boxes represent entities, and these lines represent relationships. And you can see that these lines are not all the same. Every line represents a relationship. In this case, most of them are binary relationship. But if you look at this line, this relationship between passenger and loyalty account, the cardinality is 1-to-1. So that's one type of relationship. If I look at this other one, the relationship between flight and seat, we have a line between the two, but the cardinalities are different. This is a one-to-many relationship. We've discussed this before. I'm just pointing it out again. And then if I look at these two entities, reservation and flight, it's a many-to-many relationship. So there are different types of relationships. And what we are about to embark on, we've already seen how to translate entities into the relational model, the physical model, the relational schema. Now we will have a discussion of how to take relationships and implement them in the relational schema. So this logical construct called a relation here, how do we represent it at the physical level in the relational model? Okay. And you will see in our discussion that this concept of a foreign key, which we had introduced in our very first class, the concept of a foreign key is absolutely central to capturing and representing different types of relationships. So you will see that foreign keys are used in different ways to capture one-to-one, one-to-many, many-to-many relationships. Okay, and just to remind us, you remember this relationship attributes, this concept where relationships, we obviously know that entities will have attributes. That's very natural. But we had a long discussion in the previous lecture that where we pointed out that relationships can have attributes as well, and those will need to be implemented. Okay, and in particular, this we need to focus on many to many. As we go through the discussion of implementing relationships, we will especially focus on many to many relationships because, let's see, coming back to this diagram. So this is an example between reservation and flight. This is an example of a many to many relationships. So among the three different types of relationships that I just mentioned, one to one, one to many to many, we'll pay particular attention to the many to many because there are certain complexities associated with it. Um, in particular, we will need to use something called intersection entities to represent, to implement many to many relationships from the ER model to the relational schema. And then there is a special type of relationship called between parents and child, called an identifying relationship, and we will have a discussion of it to wrap things up. And as with previous lectures, we'll use different examples to illustrate what these concepts mean. So let's get started with the foreign keys and how they are used to represent relationships. Okay. So the basic thing to remember is that a foreign key, again, this is something we mentioned in the first class, a foreign key is an attribute that is used to track instances from two different entities. So if two entities are related, so if two entities are connected by a line in the entity relationship logical model, then it means instances of one entity are related to instances of the second entity. And a foreign key is an attribute that is used to track those relationships. Okay, and the rule to remember is that the child entity receives the foreign key. Okay, and the foreign key is the primary key of the parent entity. So if you have a parent-child relationship, um, let's say we go back to this example over here. So flight and seat, you have a one-to-many relationship between these two, and flight is the parent and seat is the child. The many is the child. So the rule that we will use is the primary key of the parent becomes the foreign key of the child. Okay, so that's sort of a rule to remember. And let's see some examples, and we will be able to illustrate that further. So here is a one-to-one relationship. So you have employee and you have office, and employee is the parent and office is the child. In this case, that's what it's designated. And if you look at the cardinalities of the relationships, the line represents the relationship. These symbols at the ends of the line represent cardinalities. So we've done many examples of how to interpret what these pictures symbols mean. So let me read it out again for you. Is that one employee manages one employee manages at least 0 offices and at most 1 office. Okay, so that's the minimum cardinality. This is the maximum cardinality. Now, if you go in the reverse direction, one office is managed by at least 1 and at most 1 employee. So that's what this picture means. And we have already seen how to implement entities. So here we have an entity called employee. It has 3 attributes: the employee ID, name, and title, and every entity must have a primary key and identifying attribute. We've discussed this before. So the employee ID is the identifying attribute of the entity employee. That means if I think of all the employees that constitute this employee class, this entity class, then I can identify any one employee by using the employee ID number. That's the identifying attribute. That's the attribute that will uniquely identify an employee, any employee. Now, if I look at the entity office, it has attributes as well. It is department, section, building, and location. Those are properties of office. And as with any entity, it must have a primary key as well. There must be an attribute that uniquely identifies that entity, and that happens to be the department code. So the different offices, I can identify any one particular office by if I know the department code. So I have the primary key of that entity. Now notice what has happened over here. To actually implement this relationship, the relationship between employee and office, this shown by this line. Let me pick the pen. Look at what has happened. The primary key of the parent ended up being the foreign key of the child. Okay, so here is employee ID of, this is the primary key of the parent employee. It's been put in the as a foreign key in the entity employee. So how does that attribute help us make the connection? So obviously this line that you see in the picture, it's a pictorial representation. I can't draw a line when I implement the database. So the database has values, and all that the database software can do is look at values and use that to infer the connection between the two entities. So if I picked any office, so think of a table that represents this office, and you have these different attributes, and you have office number 1, office number 2. If I look at this last column, which has employee ID, and here is the department, the primary key. If I want to find out who is the manager for this particular department, then all I do is I go over to the last column. I see the employee ID, and immediately I can use that to connect it back to the owner. So using this employee ID, I can go back to this other table and find out the name and title of the manager. Okay, so I hope you see how this attribute called a foreign key. So you can see it's represented. Let me pick up the laser pointer again. So you can see it's represented as FK, foreign key. So I'm specifying that this particular attribute is a foreign key, meaning it is an attribute which is the primary key of the parent. The parent entity is employee, okay, and the primary key of the parent became the foreign key of the child. So here is an example. So remember we said that there are 3 different types of relationships: one-to-one, one-to-many, many-to-many. Okay, and the way we implement a one-to-one relationship, that if you have in the logical ER diagram a picture where 2 entities are connected by a single line, that's the relationship, the binary relationship, and the cardinalities that you see on the line show you that it is a one-to-one relationship. Then all you do to implement this in the relational and the physical model, the relational schema, is to take the primary key of the parent and make it the foreign key of the child. So this is sort of, imagine that it's physically sliding over. A copy of that attribute is physically sliding over and moved over to office. Okay. Now, if you think back to something we discussed in the previous, just the immediately previous lecture, we had said that every attribute in an entity has an attribute domain. Okay, so there are properties or restrictions on what values the attribute can take. Okay, so when I specify the attribute domains of these different attributes that constitute the entity office. When it comes to employee ID, okay, I will specify not only that it's a foreign key, but I will also specify that it is unique. And why will I say that it is unique? Because this is a one-to-one relationship. Okay, that means an office will have exactly one employee as its manager. Okay, and so it must be unique since it's a one-to-one relationship. I can't have two different employees being the manager for the office. Okay, so this would be unique, and also I would specify that it is non-null. This value cannot be null. Why cannot it be null? Because this picture is telling me that every office has at least one manager and has at most one manager. So an office must have a manager, and therefore when I specify this, the domain, the attribute domain that I would specify, one aspect of it, I would specify that this attribute cannot be null. Okay, and that's would be the way to implement what you see in this picture. The picture tells a story, and you have to implement that characteristic of the business operation as part of the implementation. Okay. Now let's look at another example. Here, the relationship is one to many. Remember when we discussed that little airline example, I pointed out three different types of relationships: one to one, one to many, many to many. We just had a discussion about how to implement a one-to-one relationship that shows up in the logical ER diagram. How do I implement it at the physical level in the relational schema? And we do that through a foreign key. And the foreign key needs to have certain restrictions in terms of the attribute domain. Okay, when you move the foreign primary key over to the foreign key, it has to have some constraints, as we discussed a minute ago. So here we have a relationship that is one to many. Okay, one from here to many. So the way we would read it is one job title is associated with at least zero and at most many employees. Okay, so you could have a job title that doesn't correspond to any employee. That's the minimum. So at least zero and at most many employees. Any one employee, if I go in the reverse direction, any one employee has at least one job title and at most one job title. Okay, so there's nothing magical or sacred about this maximum being one. This is a company where an employee can have at most one job title and at least one job title. So then every employee must have exactly one job title. Now, the minimum cardinality of one makes sense in the business. It would be strange for an employee not to have a title. However, this maximum value of one that an employee can have at most one job title is a characteristic of whatever business whose application whose data is being modeled. Now, I would venture to say that in most organizations, every employee has most employees have just exactly one job title. Don't have multiple job titles, but I can think of situations where an employee has multiple job titles. For instance, an individual at a university could be a professor. That's a job title, and they may also be director of a particular center. Okay, so they have two different titles at the same time. If that's the case, then the maximum cardinality should be many. So there would be a crow's foot at this end rather than a single bar. So as I've repeatedly said many times, there is nothing sacred about this relationship. All what is sacred is that the relationship, the way you represent it, the the cardinality must represent what is true in real life. Okay, so this is a one to many relationship. Let me pick up a pen. So here is one, and here's the many. So it's one to many in this direction, and the way this shows up as a picture at the logical level is that you have this line between the two entities, and the cardinalities tell you that it's a one to many relationship. So this picture How would it be represented in the relational schema? All that I do is I take the primary key of the parent. This is a one-to-many relationship. The parent is always the one, and the many is the child. This is the parent. So the primary key of the one becomes the foreign key of the many. So this foreign key that we have here, that's my attribute that connects the two entities. So a foreign key is an attribute. So this is a foreign key. A foreign key is an attribute, which is the primary key of another entity. In this case, job title. We had this discussion in the first class as well. Now let's have a little comparison. So here was the one-to-one relationship. In this one-to-one relationship, we identified the employee as the parent and the child as being the department of the office. So same rule over here. Once you have a parent-child relationship, the way you represent the relationship is the primary key of the one becomes the foreign key of the primary key of the parent becomes the foreign key of the child. Okay, so we had just discussed that. However, I had made an additional stipulation that when I specify the attribute domain, when I specify the domain of the employee ID, so I would say perhaps that it is character 5. Let's say employee IDs can only be 5 characters long. I would say that it is char 5, character 5. Okay. I would also say that it is not null because this cardinality, the minimum of 1 and the maximum of 1, tells me that every office or every department must have an employee as a parent. That's the manager of the of that particular office. So I would say not null. Okay. I would also say that it's unique. Why it's unique? Because this is a one-to-one relationship. An office can have at least one and at most one employee as the manager, no more than one. So I would say that this employee ID is unique. That's what I said a few minutes ago. Now let's come to this one-to-many relationship. So one job title can be held by many different employees. Okay, so this is the maximum cardinality is many. Okay, now every employee, if I go in the reverse direction, every employee has at least one and at most one job title. So they must have a job title. So if you think of the attribute domain for title, so when I specify the attribute domain for title, I would specify that it is not null. So I can't have an employee who doesn't have a title. So when I implement the database, I tell the database management system, hey, now you have all the different attributes for the entity employee. When it comes to this foreign key title code, it is not null. You must have a value for it. Okay. But unlike the previous example that we just discussed, I will not say, let's see, I will not say not null. Why? Because multiple employees could have the same job title. And the reason I know that that's the case is because this is a one-to-many relationship. One to many on this side. So one job title can be held by many employees. So if I look at the employee table, if I think of this entity being laid out as a table, and I go first row is the first employee, second row is the second employee, third row is the third employee, and so forth. If I go down row by row, there could be more than one employee that have the same title code. Okay, so I will specify that title code is not null. I can't have an employee who doesn't have a title, but it's not unique. There could be multiple employees with the same job title. So I hope you're seeing how foreign keys are used. This concept of a foreign key, remember just to repeat, a foreign key in an entity is an attribute that is the primary key of another entity. So that's what a foreign key is. So let me repeat again. A foreign key of an entity. So here's the entity employee. The foreign key of an entity is an attribute, in this case, okay, this title code is an attribute, which is the primary key of the related entity. The related entity's job title, and its primary key is title code. So that's the foreign key over here. Okay, so this is how we use a foreign key to implement a one-to-one and a one-to-many relationship. So now we are left with that third type of relationship, which is many-to-many. So let's see how one goes about implementing that. Okay, so if we have this, let me go back to the example that we had. So we've seen how to implement a one-to-one. So now you know how you would implement the one-to-one relationship from passenger to loyalty. You also know how to implement the one-to-many relationship between flight and seat. You don't yet know how to implement this many-to-many relationship, okay, between reservation and flight. That's what we are about to see next. Okay, so let me move over to the many-to-many relationship. So here we have a many-to-many relationship between student and offering. Just reading of this line, this relationship, the way I would interpret that is one student enrolls in at least 0 and at most many offerings. Okay. If I go in the reverse direction, one offering enrolls at least 0 students and at most many students. So if I look at the maximum cardinalities on the two sides, here's the maximum cardinality on the left, here's the maximum cardinality on the right. In both cases, the maximum cardinality is many, and that's why we say this is a many-to-many relationship. Moreover, as per our discussion in the previous prior lecture, in this case, the relationship itself has an attribute. So there is a property of it. So final grade is an attribute that is a property of the relationship between student and offering. A final grade is not a property of the student alone. A final grade is not a property of the offering alone. It is a property of the relationship between student and offering. So remember this is an interpretation of the picture that we have discussed multiple times across a previous lecture. So let's proceed on from how would I implement this if this picture were to appear in the logical entity relationship model. Now, how would I implement it in the relational schema at the physical level? Okay. So here's another example that we had discussed in a prior lecture. We have two entities here, order and product, and there's a many-to-many relationship between order and product. I know that by looking at the maximum cardinalities on the two ends. In this case, the maximum cardinalities on both sides is many. So one order includes at least one product and at most many products. One product is included in at least 0 orders and at most many orders. So looking at the maximum cardinalities on the two sides, I know this is a many-to-many relationship. Like the previous example of the many-to-many relationship between student and offering, if I look at this one, this particular relationship itself has attributes. So there's quantity ordered, unit price, discount applied. These three attributes are properties of the relationship between order and product. These are not properties of just the order or just the product. These are properties of the relationship between order and product. Okay, so let's see how we would implement this many-to-many relationships. We already know how to implement one-to-one and one-to-many. So what do I need to do different when representing many-to-many relationship? One thing you will, if you just think it through, you can't just extend that the previous technique that I can't take the primary key. Let's see, where's my pen here? I can't take the primary key of order. So my natural inclination would be take the primary key of order, make it the foreign key of product, take the primary key of product and make it the foreign key of order. So whatever we did for the one-to-many relationship, just do it twice. So do it from order to product, do it from product to order. So you would take order number and put it here. You would take item code for the product and put it over here. But that won't work. Okay? If you just think it through, that naive approach of just using the foreign key twice in those two related entities, that will not work quite well. That's very easy to see why that would be the case. So how do I implement this many-to-many relationship in the physical relational schema? Okay. The way we handle this many-to-many relationship, and there is this entity, and then there are attributes associated with the relationship. We use what is called an intersection entity. So this is the additional concept that we're introducing over here. An intersection entity is used to represent relationships between entities, and it will be particularly useful in the case of many-to-many relationships. Okay, so let's proceed with this now and see how the implementation actually works. Okay, so what is the example that we have here? So the stock picture that you see is what would appear in the entity relationship diagram at the logical level. And the way we would interpret this picture is one employee is assigned to at least 0 and at most many project tasks. Notice that the two entities, employee, project task, have their primary keys. Every entity must have a primary key. That's the identifying attribute, the attribute that uniquely identifies each instance of that entity. So in the case of project task, the task number uniquely identifies the project task. That's the identifying attribute. So one employee is assigned to at least 0 and at most many project tasks. If I look in the opposite direction, one project task is assigned to at least 0 and at most one employee. Okay, so you could have a task that has not yet been assigned to an employee. That's why the minimum cardinality is 0. Now, if this diagram is accurate representation of reality, what this is telling me is this is a company that does not assign multiple employees to the same task. Now, I could very easily think of a task in a project which has multiple employees working on it. Maybe it's a complicated task, and you have a team that's working on a particular task. It's not an uncommon situation at all. So if you could have a project task which a team is doing, then this picture would not be accurate. You would have a crow's foot. You would have a crow's foot in this on the left-hand side, and the way you would interpret it is one project task is assigned to at least 0 and at most many employees. Okay, so then in that case it would become many-to-many relationship. But here, what we have is one employee can be assigned to multiple tasks, but one task is assigned to at most one employee. More importantly, this relationship has an attribute. So as we have said multiple times, it's quite natural to think of attributes for an entity. So here you have an entity employee. It's very natural to think that, okay, an employee has an employee ID, has a name and a title and so forth. But it is less natural to think about attributes of a relationship. So if I think of date assigned and percent load, these are not properties, these are not attributes of any one of the two entities separately. So it's not an attribute of just employee, it's not an attribute of just project task. This date assigned and percent load, those two attributes, these are relationship attributes, meaning these are properties or attributes of the relationship, not of either of the two entities involved in the relationships individually. So if I have this particular picture at the logical level in the ER diagram, how do I implement it at the physical level in terms of the relational schema as relations? So you see here the two endpoints, the many-to-many relationship. Let me just write this as many to many. Okay, and I know that by looking at the maximum cardinalities. Sorry, this is a one to many. I look at the, let me just erase this over here if I can. So this is a one to many relationship, but it has attributes. Okay, so how do I implement this in the relational schema? Let me pick up the pointer again. So what I do is, in order to implement these relationship attributes, the first thing I do is I introduce what is called an intersection entity. So you see this new entity that was not there in the at the logical level. So I give that every entity must have a name. So I give this entity a name. I call it task assign. Okay, and it should be an intuitive name. So the name of the entity tells me that it's a connection between the employee and the project task. So I'm assigning a project task to an employee. Okay, so here is the intersection entity, and notice what is important is the attributes of the intersection entity. This box is the intersection entity. These two attributes are the two relation attributes. So these two, data sign percent load. So an employee, let's say, spend 30% of their time on one particular project, 20% of the time on another project task. Okay. So the two relationship attribute became the attributes of the intersection entity. Okay, so this box over here is the intersection entity. Now, what is interesting is the relationships between the intersection entity and its two connecting entities. So you have employee and project task just as before. So you had the original one-to-many relationship. Here is employee, here is project task, here is employee, here is project task. That way they are the same. Okay. The important thing here is this one relationship over here, this one-to-many relationship from employee to project task has been broken down into a pair of relationships over here. So you have one relationship between employee and the intersection entity. You have another relationship between project task and the intersection entity. Okay, so it's been broken up into a pair of relationships. Okay, so it's a pair of parent-child relationships. So when you have this kind of a setup structure in the logical level, when we're trying to implement it at the relational in the relational model, this particular what the technique that we use is with this intersection entity. So let's focus on the cardinality. So this one relationship has been broken down into a pair. Okay, so let's look at the first one, the relationship between employee and the intersection entity. Okay. So we have one employee is assigned to at least zero and at most many intersection entities. So this left-hand side is a reflection of the cardinalities going from employee to project task, going from employee to project task. Now, if I look at the second relationship over here, the cardinalities of the second one, they represent the cardinalities going in the opposite direction, from project task to employee. So a project task is assigned to at least zero and at least and at most one employee. So that's the interpretation over here. One task, one project task is assigned to at least zero and at most one task assigned. Okay. Now notice in the reverse direction, after in the discussion that I just had now is the cardinalities from employee to task assigned and the cardinalities from project task to task assigned. So now we have to sort of finish off the discussion by looking in the opposite direction. So the cardinalities always, you must look in both directions, right? We've seen that numerous times up to now. So I start from this intersection entity and go in the reverse direction. So this intersection entity that reflects the attributes, the task assigned, this particular intersection entity, one of the assignments is associated with at least one and at most one employee. Do you see this is a mandatory relationship? Okay. Similarly, this intersection entity is associated with at least one and at most one project task. So it is, if you think of in terms of pictures, just see what has happened, what cardinality has migrated where. So this cardinality has migrated over here, and this cardinality has migrated over here. Okay, so And the reason we are going through this intersection entity is that you will see in a minute that we can again use our good friend, the foreign keys, to implement it. So as of now, this picture that you are seeing, it is still at the logical level, the logical and entity relationship level. We must, to get it to be implemented at the physical level, the physical relational schema, I will again somehow need to use foreign keys to make that connection, because as far as the database is concerned, I can't just show lines. I can't show lines in the database. I have to use the data itself to sort of mimic the lines. That's basically what we will end up with. That's what foreign keys allow you to do. So let's see what would be the next step once we have this. Okay, once we have used this intersection entity to represent uh, uh, relationship attributes. Okay, let's proceed now. How would we implement this particular uh, intersection entity and its relationships with the two connecting entities, employee and project? So here we go. First, we assign parent-child. So here's a one-to-many relationship from employee to the task assignment, this intersection entity. The one always is the parent, and the many is always the child. So here is a parent-child relationship. Now, in this case, so you have a one-to-one relationship. In a one-to-one relationship, typically you have a choice of calling one of the entities a parent and the other one a child. In this case, you don't. Even though this is a one-to-one relationship, the intersection entity is always the child. Okay? So this task assigned, this intersection entity is the child, and project task is the parent. Okay. So now that we have this, once we have a parent-child relationship, we have already discussed this a few minutes back. How would I use foreign keys to represent this parent-child relationship? So the primary key of employee is employee ID. Every entity must have an identifying attribute, a primary key. The project task, its primary key is task number. Okay, so you know by now what the next steps would be to implement the relationship. The primary key of the parent becomes the foreign key of the child. So task number would come in over here, employee ID would come over here, and that's how we would use foreign keys to represent these two lines. Since I cannot actually just draw pictures in the physical database itself, you mimic those lines by using foreign keys. That's what we are about to do. So next, so the first step, I take the primary key of employee, so this is the primary key of the parent, and it becomes the foreign key of the many. So you see I've taken this employee ID and moved it over here, and I've designated it as a foreign key, FK. Okay, so that's one step. And I think you can guess what will happen at the next step. I take the foreign key of the parent, in this case task number, and I move it over as this is the primary key of project, task number, and I move it over as a foreign key of the child. So here's task number. So I have two foreign keys. So since there are two relationships in this picture, so we have two foreign keys. So task number connects this intersection entity to project task. Employee ID connects connects the intersection entity back to employee. Okay, now elaborating on this a little more, if I think about what kind of attribute domains will this have, what kind of restrictions would exist on the task number attribute and the employee ID attribute. Okay, so whether it would be text or numeric depends on how task numbers are set up. So that's less of interest to me. One thing which is of interest is knowing that these relationships exist. So one employee could be assigned to at least 0 tasks, project tasks, and at most many. Since an employee need not be assigned to any project task, this employee ID could be null. Okay, you must allow for the fact that this employee ID could be null. So they're not assigned to any particular task. Okay, and in this case, the task number, if you come back to the left, a task number could be assigned to at least 0 employees and at most 1 employee. What this simply means is there could be project tasks that have not yet been assigned to any particular employee. Okay, so just from this picture itself, task number could possibly be null because you could have a project task that is not assigned to any employee yet. However, we are not quite done. Notice that every entity, in this case, this is an intersection entity, every entity must have a primary key, right? We know that by now about the property of a relational model. We don't have, at least I haven't drawn any primary keys yet. So that's another step that we need in order to complete the transition, complete the implementation of the. So this particular picture was the logical model, and we are gradually working our way to the physical implementation in the relational schema. So here is the first step, identifying parent-child relationships in the picture. The next step was using foreign keys to capture these parent-child relationships. There are 2 relationships, so there are 2 foreign keys. Now, to complete this picture, where's the primary key of assign? So I need to somehow identify what is the primary key of this intersection entity. So what we are doing is we are saying that employee ID and task number together will be the primary key of this intersection entity. So here is an example of a composite primary key. All right. So if you look at these 2 lines over here, you can see PK, PK, FK1, FK2. You don't see PK1 and PK2. This is extremely important. So you don't have 2 primary keys. You can never have 2 primary keys for an entity. Only one attribute that uniquely identifies instances of the entity. So if I give you task number and employee ID, you can identify any record in this intersection entity. Now notice one thing, a few minutes back, I had argued that employee ID could be null because you could have an employee who has not been assigned any task because the minimum is 0. Similarly, you could have a project task that is not been assigned to any employee yet. The minimum cardinality is 0. So I had said that employee ID. So here's what I had said that. I could have said that the foreign keys. Sorry, here's the 2 foreign. I had said that employee ID over here and task number over here could be null when I specify the attribute domains. However, now that I have specified that task number and employee ID are jointly the composite primary keys cannot be null. If you have a null, if a primary key can be null, you cannot uniquely identify every instance of that particular entity. So as soon as I specify that task number and employee ID are together the primary key, then I have to also specify that task number and employee ID cannot be null. Okay, so it's very important to remember that when I look at these 2 attributes, each of them separately is a foreign key. I have 2 foreign keys. Why do I have 2 foreign keys? Because I have 2 relationships. A foreign key connects records in associated entities. So employee ID allows me to associate instances of this intersection entity to instances of employee. Similarly, task number allows me to connect instances of this intersection entity with instances of project task. So they're 2 separate foreign keys. That's why you see FK1 and FK2, but you don't see PK1 and PK2. So these are not 2 primary keys. This is one composite primary key. Okay, I hope you see the distinction, the important difference between this primary key and the foreign key, and the important distinction in their specification. So let's follow along in a similar vein. So here again you have relationship attributes. So just to recap, here you had an example where you had the logical model entity relationship diagram, and you had a relationship with relation attributes that are properties of the relationship. However, the relationship was one-to-many. So anytime you have relationship attributes, the way you implement that is by using intersection entities. And here we used an intersection entity to represent a one-to-many relationship that has relationship attributes. Okay, so now let's look at a more complex situation. Here again, we have relationship attributes. So we have these two attributes that are properties of this relationship will include. But in this case, the relationship is many to many. Okay, so a one order includes at most many items, and one item is included in at most many orders. That's why. So if you look at the maximum cardinalities on the two ends, this is a many to many relationship. How do I implement this picture in the ER logical model? How do I represent it in the relational schema? So here are the two entities, order and item, that have a many-to-many relationship between them. You can see the primary keys are identified over here, the identifying entity. So we have a relationship attributes. First step, create an intersection entity. So here's the intersection entity, and I stick the two relation attributes, the relationship attributes. I take them and put them here, just the same as what I did before: quantity, order, and unit price. Okay. So now that I have the intersection entity, this one many-to-many relationship is broken up into two relations. So very similar to what we just did. What is different is the cardinalities at the two ends. So just quickly look back to the picture. Here again, you have two relationships, but you have a one-to-many relationship over here and a one-to-one. All right. So in this example, what has happened is a many-to-many relationship between order and item has been replaced with an intersection entity and a pair of one-to-many relationships. So this is a many-to-many relationship. This has been broken down into a pair of one-to-many relationship. Okay, so you can see the same transfer. So this cardinality, the minimum and maximum cardinality over here, came here, and the minimum and maximum cardinalities came over here. Okay, so if you had to express this in words, the way you would express this implementation in word is one order is associated with at least one order item and at most many order items. Okay. Similarly, one item is ordered in at least 0 orders and at most many orders. Okay. And on the left hand side, so one order item, this particular intersection entity, is associated with at least one and at most one orders. It's the same thing on the right hand side. One instance of an intersection entity is associated with at least one and at most one item. So this is a mandatory relationship. Okay. So now that I have this pair of one-to-many relationships, I think you can guess what the next step would be. The next step would be to identify parent and child. If you have a one-to-many relationships, as I said a few minutes back, if you have a one-to-one relationship, you have a choice of calling one the parent and calling the other child. But in this case, we have a many-to-many relationship, and we decomposed it into a pair of one-to-many relationship. Okay, so the one is always the parent, the many is always the child. The one is the parent, the many is the child. So we have a pair of parent-child relationships. Now that I have this, using the foreign key concept would be just the same as before. The primary key of the parent becomes the foreign key of the child. So order number, which is the primary key of order, becomes the foreign key of order items. Similarly, the product number of item, the primary key of the parent, becomes the foreign key of the child. So there are two foreign keys because there are two relationships. One foreign key represents one relationship. So here's fk1, foreign key1, foreign key2. The only thing that's left now is I can't have an entity without a primary key, without an identifying attribute. And I think you can guess now what I could use the order number and product number together as a composite primary key. And that is what you're seeing here. So this step has pretty much identical to what we discussed before for the one-to-many relationship, which had relationship attribute. So here you're saying that this intersection entity called order items, the primary key of this entity is the joint, these two attributes, order number and product number joint. So you see PK, that means these two together are the primary key. You will never see PK1 and PK2. An entity cannot have more than one primary key. So it has one primary key which is composite, these two attributes composite, and it has two foreign keys, FK1 and FK2. FK1 connecting it to order and FK2 connecting it to items. So here we have this implementation that's done. Now, if we had a ternary relationship, so these, just imagine, I think I told you several times that 90% of the time, the relationships that you will be seeing in an ER diagram and which you'll be implementing are a binary relationships. But once in a while, you end up with ternary relationships that you're seeing over here. These two examples we had used in a previous lecture. So you have a prescription. So you have these three attributes: prescription date, daily dosage, and fill date. So these are relationship attributes. These attributes are properties of the relationship among these three entities, not any of these entities by themselves. Okay. So as with the same logic, if you have a relationship attribute, first set up an intersection entity. So here's this intersection entity. So this type of a picture you would see in the logical entity relationship diagram. Then moving over to the right is how I would implement that in the relational schema at the physical level. First step, I create an intersection entity to capture the relationship attributes. Okay, so here I have these three attributes over here. And then you have the cardinalities of the three separate relationships connecting the three entities to the intersection entity. Okay. And then I could use so the primary key of patient would transfer over here, the primary key of medicine would transfer over here, and the primary key of doctor would transfer over here, and I would use that same logic to go ahead and complete this particular implementation at the. So we'll complete our discussion of the transition or the implementation of relationships in a logical ER diagram, one-to-one relationship, one-to-many, many-to-many. So we saw how the foreign key is really the only tool you have to build relationships, and we saw how to use this concept of a foreign key to represent those three different types of relationships. Okay. Now, in the process, we talked about foreign keys and primary keys. So there's one other type of key that we need to identify or to discuss to wrap up this discussion, and is something called a surrogate key. Okay, and I think you can imagine what it might be. Surrogate is something that substitutes for something else. Okay, um, so that's what the term surrogate means: substitute for. Okay, so what's a surrogate key? It's a separate key um, when you don't have any good candidates for primary key. Typically you use surrogate keys when you have a composite primary key and it's too big, meaning the composite key consists of too many attributes. Having a composite key that has two attributes, or at most three, is okay, it's manageable. But if somehow you end up in a situation where you have a composite key that is 4, 5, 6 attributes long, it just becomes very unwieldy to identify instances of that entity and so forth. Okay, so a surrogate key is really just a randomized code that is generated and is used as a primary key. Okay, so so for intersection entities, surrogate keys are typically introduced when primary keys exceed 3 attributes. So So we'll see. Now, here are examples of situations where uh, uh, a good primary key is not available. So if I don't want to show student ID number, or if I don't want to show a credit card number, then I might generate a random fixed code and use that as a surrogate key. So let's look at one example where I think this example will show fairly clearly what is a surrogate key and when is it used. So here I have a table, a relation, where the primary key consists of 4 attributes. So this is a course offering. Okay? So a course offering is a section of a course offered in a particular semester. So I have the course title, the course prefix, and I have the course number, I have the section number, and that's not enough. I also have to identify the semester in which is being offered. So do you see it says PK, 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 PK? That doesn't mean these are 4 primary keys. It simply means that for this particular table relation called offering, the primary key is a composite primary key consisting of 4 attributes. Okay, this is very unwieldy to handle in the when managing the database. So instead of using this huge, large composite primary key, we create a surrogate key. In this case, it's called a course CRN number. I think all of you, when you've registered for your courses, you have seen the CRN that is associated with every course. So this number that you see over here, C123, C234, this is system generated. This has no bearing with the values that you see in these 4 columns. Okay, so instead of having a composite primary key, I have a simpler 1 attribute primary key that's a surrogate for this composite key. Okay, and these values are system generated. So this is an example of a situation where you would use a surrogate key, and it also shows you what a surrogate key looks like. Okay, these are usually system generated values. Here's another example. You have a reservation, a flight reservation. So what might the attributes be? You have the airline, the flight number, the date of the flight, the name of the passenger, and the seat number. So the primary key what would be the primary key? The seat number is obviously not a good primary key. The passenger name is not a good primary key. Okay, and also if I look at all 5 of them together, United Airlines Flight 117, date, passenger, and seat 5C. Uh, having 5 attributes together is really not not a good. This too big a composite primary key. So what do I do to handle that? I have a surrogate key, and a typical surrogate key is the ticket number. This ticket number usually is system generated, and they have no bearing with the values of the other composite primary key elements. So this ticket number is an example of a surrogate key. It's a primary key, 1 attribute, which is a substitute as a surrogate for a fairly complicated composite primary key. Okay. Let's see another example where even though the primary key is only 2 attributes, is order number and product number. This is an example we encountered a little while back. Why we might want to use a surrogate key. So suppose I have this particular implementation. There is a many-to-many relationship from order to item. So we have, and there are this relationship as attributes. So you have these 2 attributes, quantity ordered and unit price, as the properties of the relationship between order and item. And so we created the intersection entity and set up those 2 relationships, and etc. etc. Okay, so we have the parent-child and the parent-child relationship. So you have a composite primary key, which is the composition of the primary key of both parents. Okay. Now notice that depending on how the business run things, suppose any one particular order, somewhere down the road, after having placed the order, then the quantity ordered has changed. So let's say I ordered 3 windows from Home Depot, and they're put in that order, and then in the process of fulfilling it, one day later I call them and say, oh, I made a mistake. Please don't send me 4, send me 3 windows. So the quantity ordered has changed. Okay. So how might I represent that in the database? I might keep the order number the same, and I just change the quantity ordered from 4 to 3. So that's one way to do it. However, what the company might want to do is create a new intersection entity. Same order number, same item number, product number here, but you have a new record. So the reason this might be helpful is it gives you a history. So if the customer calls back later and said, "Hey, you only sent me three windows," and if you have the history, the company can respond by saying, "Hey, you yourself reduce the number from 4 to 3." Now, if you don't keep both the changes, then the system lost the memory that 4 windows had been ordered earlier. So that would be the value of having the revised order stored as a separate entity. Now, if I have a new uh, entry in this intersection entity, it would have the same order number. So the revised value, this quantity changing from 4 to 3, you could imagine that there are 2 records in this intersection entity, both of which have the same order number and product number. So that's not good. You can't have an entity with repeated values for the primary key. Okay, so in this case, the composite key of order number and product number is insufficient. So the business wants to keep a track of the history of any changes to any orders, not just the latest value. The history can help for integrity reasons, for resolving questions from customers or resolving lawsuits and so forth. So history might be important. And here, if the business operates by maintaining history, this composite key of order number and product number is insufficient. That will not do the job for us. So how do I handle that? The way I can handle that is by creating a surrogate key. So I have this surrogate key called order line item. Okay. So now just think. So these 2, order number and product number, remain as foreign keys, but they are no longer participate as a composite primary key. That's the change. So here's what was before. Here's what is now. We now have a surrogate key. So imagine what this does is. So an order is placed to today. It has an order number, and an order is placed for 5 different items. Okay. So and we have this intersection entity filled out for those five items, and then 5-6 days down the road, one of the for one of the items, the order quantity is changed. You say some 4 to 3. What would happen is I would put in a new row, a new record for this particular entity. So a new instance of an entity, not an entity class, but an entity instance, and I would simply have a different order line. So this primary key value would be different for this revised value. So the original order, which had 3 items, four as the quantity ordered for a particular product. Now if I revise it, that old value of 4 can still remain, but I will have the new revised value of 3 with a different order line number, so the different value of the surrogate primary key. So I hope you're seeing how in this particular instance, the use of a surrogate key allows me to capture history of the transactions, whereas without the surrogate key, I would not have been able to do that. Okay, in terms of implementing an logical model, entity relationship logical model, and coming up with a relational schema, the physical model, there is a refinement of entities that we need to discuss, namely something called weak and strong entities, two different types of entities, weak and strong. What do they mean? Why do they exist? Why do we need to bother with them? Okay, so we've already seen so far examples of parent-child relationship. So if you have a one-to-many relationship, the one is the parent, the many is the child. If you have a one-to-one relationship, you typically have a choice of calling one of them the parent and the other one as the child. If you have a many-to-many relationship, once you put in an intersection entity, both those other entities become parents, okay, and the intersection entity becomes the child. So a many-to-many relationship is represented as a pair of one-to-many relationships. So let's, once I know that, let's focus on one-to-many relationship. So a child and parent, once you have a parent-child relationship, a child entity is also called a weak entity because the child cannot exist without related data in the parent. So when you have a parent-child relationship, the child cannot exist without a related entry in the parent. Okay? And the parent entity is called the strong entity. So what would be an example? So for the airline example you had seen, you had flight and seat. Okay? So if you think of, let's see, so if I have flight and I have seat. So one flight has at least one and at most many seats. One seat is associated with at least one and at most one flight. Okay. Now, if I have a seat cannot exist without a flight. Okay. So this is the parent. This is the child. The child would be called a weak entity, and the parent is a strong entity. So with the examples that we have over here, the relationship between room and building, if you have a relationship between room and building, one building has many rooms, the parent would be building and the child would be room. Similarly, if you look at the relationship between these two entities, textbook and edition cannot exist without a textbook. So you have a one-to-many relationship from textbook to edition. Textbook would be the strong entity, the parent entity would be the strong entity. In this previous the prior example, the relationship between building and room. Building is the parent, room is the child. So building would be the strong entity, that's the parent, and room would be the child entity, and it would be a weak entity. Okay. So now that we have discussed strong entities and weak entities, and we said that the child entity, the weak entity, cannot exist without the parent. There are little nuances to weak entities. So here we can see something called an ID dependent weak entity. Okay, fancy name, what does that mean? So let's look at a specific example. Here I have two entities. This is a logical entity relationship diagram. I have an entity called student and I have an entity called car. Okay. So what is this picture telling me? So I have this one student owns at least 0 cars and at most 1 car. Okay, so this is a one-to-one relationship. If I go in the reverse direction, 1 car is owned by at least 1 student and at most 1 student. Okay. Now it might seem odd. I could have a student who doesn't have a car. Okay. Now, why maximum of 1 car? Presumably, this is a campus. Typically, parking is difficult on campus, and many universities have a rule that maybe freshmen cannot keep cars, and even the seniors, those who can keep cars, they can't keep more than 1 car. So they're limited to 1 car on campus, and that's what might make sense as an interpretation of this picture. Why is it that one student or can own at most 1 car? There is probably a restriction on campus because there's no parking space. In any case, you have a one-to-one relationship over here. Student is designated the parent and the car is the child. Okay. Typically when you have a one-to-one relationship, uh, either one of them could be called a parent, the other one could be called a child. But in this case, since car is optional for student, it makes sense for student to be the parent. Okay. So as with previous discussions, every entity must have a primary key. I have student ID as the primary key of student, and I have the car make and model. These are the attributes of car. Now, what should be the primary key of car? Okay. So every entity must have a primary key. Now, notice that in this case, we're making the student ID as the primary key of the car. Why? Because a student can have at most one car. So this attribute, the fact that the primary key of student has become the foreign key of car. This is what connects a car to a student. So if I think of this entity called a car, and the way it would be represented as a table is you could have one car, second car, third car, and then you have these different attributes of the car. So the primary key is this, since a student can have only one car, okay, so the first car, its primary key is the student number. I can safely put that because I know there will not be another car with the same student number. A student is allowed to have at most one car. Okay, so here is your first car, here is your second car, here is your third car, the student numbers corresponding to the three different cars. So as soon as I see the student number for a particular car, I can use that to connect back to the student and find out the details of the student. Okay, so here you have a parent-child relationship, and we've said that a child cannot exist without a parent. So if you have a car, there must be a parent. Must be a student as a parent. And you can see that from the mandatory uh, cardinality as well. Okay, so in this case, this type of a weak entity, this child entity called a car, is what is called an ID dependent weak entity. So here's ID dependent weak entity. It is to this name, this term is used to signify the fact that the primary key of this child is also derived from the primary key of the parent. Okay, so student number is a primary key, student ID is a primary key for student, it is also the primary key for car. Okay, so this is an example of an ID dependent weak entity. All right. Here is another example of an ID-dependent weak entity. We have a one-to-many relationship in this case over here, an entity called textbook, an entity called editions. So one textbook has at least one and at most many editions. One particular edition is associated with at least one and at most one textbook. Okay, so you have a textbook serial number, book title as the as attribute. The primary key, every entity must have a primary key. The textbook has text serial number as the primary key. Now notice what is the primary key of editions. So you have these two attributes that are underlined, and notice what's the comments that are written next to them. One says PK and the other says FK1. Why FK1? That means there is one foreign key, and that makes sense because there is only one relationship in the picture that you are seeing. Relationship from textbook to edition. That's why FK1, only one foreign key. Now remember we said that any entity can have one primary key. So here you have PK. This doesn't mean that they're two separate primary keys over here. It simply means that these two attributes together constitute the primary key. So now let's parse this composite primary key. One piece of that composite primary key is text serial number. The other piece is edition number. Okay. So notice that this text serial number is part of the primary key of the child. It is also the primary key of the parent. So here is the situation. Again, it's the same as before. The primary key of the parent is now a part of the primary key of the child. So this is also an example of an ID-dependent weak entity. ID-dependent weak entity. So what is the distinguishing feature of an ID-dependent weak entity? First of all, we must look at a weak entity. So that's the child. So here's the weak entity that we are looking at. What makes this entity of an ID dependent weak entity is that its primary key, at least as part of the primary key, is also the primary key of the parent. Okay, so it's the fact that the primary keys match or shared is what makes it ID dependent. So the primary key of this child depends on the ID of the parent. Okay, so this is ID dependent. Uh, Now, since you have an ID dependent weak entity, obviously there must be something called a non-ID dependent weak entity. How are they different? How are they different? A non-ID dependent weak entity. Remember, weak entity is a child. Okay, so a non-ID dependent weak entity may have a single or composite identifier that is primary key, but the identifier of the parent will be a foreign key. The foreign key is not part or all of the primary key. Okay. So in this case, we say it's weak but not ID dependent. So a lot of detail over here. Let's look at some specific example. I think that should clarify what's the distinction between an ID dependent and a non-ID dependent weak entity. So by the way, an identify if a weak entity is ID dependent, its relationship is represented by a solid line. If a weak entity is non-ID dependent, the relationship is represented by a dashed line, solid line, dashed line. And remember, a line represents a relationship. Okay. So let's go back to our student and car example. Okay. So remember, this was a weak entity because car is the child, and it's an ID dependent weak entity because the primary key of the child is in fact the primary key of the parent. Okay, so here you can see student ID is the primary key of the child itself. So this is an ID dependent weak entity. Here's the second one. So we have student and course. And here's the intersection. By now you know how to implement a many-to-many relationship. One student can take many courses, one course is taken by many students. So this is a many-to-many relationship between these two entities. The way they are implemented is by putting in an intersection segment and replacing the many-to-many relationship between student and course by a pair of one-to-many relationship. Okay. Now, look at what has happened to the primary key. So if I look at the intersection entity, I have two attributes here, G number and course number. And these two together are the composite primary key of the intersection entity. So you can see on the left-hand side it says FK2, FK1. That means there are two separate foreign keys here, but you have PK, PK. That means these two attributes together form the primary key. So what is the situation that you have? You have a child. This is a weak entity, but the primary key of the parent is either a part or in whole, like you saw before, is a part of the primary key of the child. So if I look at the primary key of the child, either part of it or all of it is also the primary key of the parent. So this is an example also of an ID dependent weak entity. Okay. Now let's look at a third example over here. So student and registration, course schedule and registration. So this is so one student can be registered for many offerings, and one offering could register many students. Okay, so there is a many-to-many relationship between student and course offering, the course schedule. All right, and it is represented by a pair of one-to-many relationships. So here's first one-to-many relationship from student to the intersection entity, another one-to-many relationship from course schedule to the intersection entity. And the primary key of the intersection entity is a composite primary key, G number and CRN. Okay, so you can see that the primary key of the weak entity, in this case the child, in whole or in part, is the primary key of the parent. So you can see G number showing up here. You can see CRN showing up here. So this is an example of an ID dependent weak entity, and that's why the relationships are drawn as solid lines. Okay. Now let's look at these other two, course and semester. So one course could be offered in multiple semesters, and if I pick any one semester, it could have multiple courses on its schedule. So there's a many-to-many relationship between course and semester. Okay, and as with previously we've seen, to implement many-to-many relationship, we set up an intersection entity, and inside the intersection entity, you have attributes. These are attributes of the relationship um, between the two entities that have a many relationship. Now let's look at the attribute. We have a primary key, which is a surrogate primary key. Remember we talked about CRNs a little while back. What's the use of it? What is a surrogate key and when is it used? Now, if you look at all these other attributes over here, you have section, number of students, and so forth. And then you have a bunch of foreign keys. So you have course number, semester. Semester and year are not semester and year are foreign keys, as is the course number. And then you have subject code. So what are these attributes telling us? So course number, this particular attribute connects to course. Subject code, this foreign key connects to code. Remember, foreign keys are the only tool you have to implement relationships. So you just use them differently for representing different types of relationships. So you have semester, this foreign key that connects to the entity called semester here, and you have year, which connects it to semester over here. So notice that the primary keys of the parents, in this case semester and course, do not appear in the primary key of the intersection segment. So this is a child. This intersection segment is a child course schedule, but the primary key of the parents do not appear either in whole or in part as the primary key of the weak child. Okay. This is quite different from registration. In registration, the primary key of the weak entity is in whole or in part the primary key of the parent. Okay. So here, the primary key of the parents are foreign keys in the intersection entity alone, nothing else. Okay, so that is why these two relationships are drawn by dotted lines. Okay? So this is in this particular guy, course schedule in the relationship between course and semester. This intersection segment is a non-ID dependent weak entity, whereas registration is a ID dependent weak entity. Okay. So let's sort of recap all the different things that we have learned in this last two lectures. So we were seeing how to translate logical ER to the physical relational schema, and in the process we talked about attribute domains. That concept allows us to translate entities and their attributes to the relational model. And in that process, we talked about primary keys, what's a candidate key, and what are the criteria that should be used to pick a primary key from a list of candidate keys. Then we talked about foreign keys and how they are the only mechanism that you have to link, to represent relationships among different entities. Okay. Then we introduced this, or rather discussed this concept of relationship attributes, many-to-many relationships, surrogate keys, identifying relationships. So once you have made, let's go back to our original, the airline example. Okay, so here with the once all the translations have been done, all these relationships that you see over here, the one-to-one relationship, one-to-many, and so forth. So these relationships would get implemented in the relational schema, and then you're ready to actually implement the database. So in the next module, in module 2, we will see how after we have come up with the relational schema, after we have come up with this picture over here, tables, the relations, their attributes, foreign keys, primary keys, and so forth. Once we have done that, we will see how to use the language called SQL to actually put this on the computer, how the database management system, this was the data, how this particular software over here would help us in taking this implementation that we have come up with and actually putting it on the on the computer, okay, on the hard on the storage drive. So with that, this set of lectures concludes our discussion of the data modeling process. Okay.